Tonight we're going to take a closer look at something that on the surface seems almost embarrassingly simple, yet the moment you start pulling on the thread, it unravels into one of the most uncomfortable truths about our existence as a species. We're going to chase down a single, blunt question. How fast could we actually cross a single light year? Not in some imagined future. Not with technology that lives only in screenplays and fever dreams. With the machines we have right now. In this exact moment in history. And by the time we reach the end of this conversation, you're going to walk away with a very different feeling about those tiny pinpoints of light overhead. Because once you understand what they really are, and how impossibly far they sit from us, the night sky stops looking like a window and starts looking more like the bars of a cell. Before we get going, if you find yourself hooked by the strange, vast, and often unsettling realities of the universe the way we are, take a quick second to leave a like or hit subscribe. It costs you nothing, and it helps us reach more curious thinkers who want to wrestle with these questions alongside us. Now, let's begin. We need to start with what a light year actually is, because almost everyone gets this wrong from the first sentence. A light year isn't a unit of time, despite the way the word is built. It's a unit of distance. Specifically, it's the span that light covers during the course of one full year. And light, as it turns out, doesn't crawl, it hurtles. It tears across reality at a speed so absurd that our intuitions essentially shut down trying to picture it. Light moves at roughly 186,000 miles every single second. Let that figure sit in your mind for a moment. In one heartbeat, light could loop around the Earth's equator about 7.5 times. In that same single second, light covers more ground than most people will physically traverse in their entire lifetime, even if they spent every spare moment of it traveling. By the time your eyelids meet during a blink, light has already raced a distance roughly equal to 3 full circuits of our planet. Now multiply that staggering speed by the number of seconds inside a single year. 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. Run the math, and you end up with about 536,000 seconds packed into one orbit of our planet around the Sun. Light cruising at 186,000 miles per second across all those seconds covers a distance of roughly 5.87 trillion miles. And that's the question we're sitting with tonight. How long would it take for us, with our blunt, rocket-shaped technology, to span that 5.87 trillion mile gap? Let's start with the absolute champion, the fastest human-built object ever to slice through space, the Parker Solar Probe. Launched in 2018, the Parker Solar Probe is a NASA mission designed to study our own star up close. Its purpose is to dive deeper into the Sun's environment than any spacecraft ever attempted, plunging through the corona, the outer atmosphere of the Sun itself, gathering data on solar wind and the magnetic forces that shape it. To pull off that kind of approach without simply melting into vapor, it has to move with absolutely punishing speed. At its peak velocity, the Parker Solar Probe blazes along at roughly 430,000 miles per hour. That's the fastest velocity any human-made object has ever achieved, the equivalent of about 119 miles per second. To put that against something familiar, a bullet from a high-powered rifle leaves the barrel at around 1 mile per second. The Parker Solar Probe is moving 119 times faster than a bullet, and even with that ferocious pace, it remains laughably, painfully slow when held up against light itself. Light moves about 560 times faster than our quickest spacecraft. So what does that mean in practical terms? How long would the Parker Solar Probe need to cover 1 light year? 1 light year is that 5.87 trillion mile distance we calculated. At 430,000 miles per hour, that journey works out to approximately 560 years. Let me try to anchor that number to something graspable. 1600 years is roughly the time that has passed between the collapse of the Western Roman Empire in the year 476 and today. It's essentially the entire arc of the Middle Ages stitched together with the modern era. To merely reach Proxima Centauri, the closest star beyond our own Sun, sitting about 4.25 light years away, this same probe would require more than 600 years of continuous travel. By the time it crossed that distance and arrived, humanity might be extinct, scattered across the galaxy with technology that makes the Parker Solar Probe look like a wooden ox cart. evolved into something we wouldn't recognize as human at all, or possibly still right here on Earth, having long since forgotten we ever launched the thing in the first place. The mission would have outlived not just generations, but entire civilizations. You might be sitting there thinking, fair enough, but the Parker Solar Probe wasn't built for interstellar travel. It was built to swing close to the sun. What if we engineered a craft specifically for crossing the gap between stars? What if we took our absolute best rocket science and tuned every parameter for raw speed? Let's bring in the Voyager probes. Voyager 1 and Voyager 2 both lifted off in 1977. Both are still operational, still whispering data back across the void after more than 45 years of continuous flight. Voyager 1 holds the title for the most distant human-made object from Earth, currently somewhere around 14.5 billion miles out, well past the orbit of Pluto, drifting through the actual interstellar medium beyond the heliopause. Voyager 1 is moving at roughly 38,000 miles per hour relative to the Sun. Considerably slower than the Parker Solar Probe, but absolutely staggering by the standards of anything you experience on Earth. At that velocity, Voyager 1 could cover the distance from Los Angeles to New York in about 4.5 minutes. But how long would Voyager 1 need to cross a single light year? At 38,000 miles per hour, that comes out to about 17,600 years. More than 11 times longer than the Parker Solar Probe. The Voyager probes are extraordinary achievements. They've performed beyond anyone's wildest expectations. They've sent back jaw-dropping images and measurements from Jupiter, Saturn, Uranus, Neptune, and now from interstellar space itself, the first emissaries of our species to truly leave the gravitational neighborhood of our star. But they're slow. By cosmic standards, they're glacial. Let's try another approach entirely. What if we tossed chemical propulsion aside and reached for nuclear power? Nuclear rockets have been studied extensively for decades. The basic concept is straightforward enough. You use a nuclear reactor to heat some kind of propellant to outrageously high temperatures, and then expel that propellant out the rear of the spacecraft. In theory, this allows you to achieve substantially higher exhaust velocities than any chemical rocket can manage. Back in the 1950s and 60s, there was a project called Project Orion. The idea was nothing if not bold. Rather than relying on a conventional reactor, you would actually detonate a series of nuclear bombs behind the spacecraft. Each blast would slam against a colossal pusher plate equipped with massive shock absorbers, and the recoil would shove the vessel forward in great surging leaps. It sounds completely insane. In many ways, it is completely insane. But the underlying physics genuinely works. Calculations from the engineers who studied it suggested that an Orion-style craft could potentially achieve speeds in the range of 3 to 5% of the speed of light. Let's be generous and assume the upper bound of 5%. At 5% the speed of light, crossing a single light year would take about 20 years. Now that, suddenly, is something we can actually conceive of. That fits inside a human lifespan. If you boarded such a vessel at 25, you would step off at 45, still young enough to explore, still vital enough to contribute to building a colony on the other end, still possessing decades to witness whatever unfolded after arrival. But here's the catch. Project Orion was never built. It was studied with enormous rigor. Engineers ran every calculation. They worked out the dimensions of the bombs, the mass of the pusher plate, the precise trajectory through space, the radiation shielding needed to keep a crew alive. They drafted life support concepts. They modeled the pulsing acceleration profiles. But the thing was never assembled, and it almost certainly never will be, at least not using actual nuclear weapons. The barrier is partly political and partly practical. Launching nuclear bombs into orbit is forbidden by international treaty. The Partial Test Ban Treaty of 1963 and the Outer Space Treaty of 1967 both place explicit prohibitions on the deployment of nuclear weapons in space. Even setting aside those legal walls, the engineering hurdles remain enormous. You would need to carry thousands of nuclear devices with you. Each detonation would have to be timed and positioned with surgical precision. A single malfunction could vaporize the spacecraft. The radiation exposure for any crew, even with elaborate shielding, would still be considerable, and the cost would be quite literally astronomical. So Project Orion remains a fascinating thought experiment, A theoretical possibility with the math worked out, but not something we'll be assembling on any nearby timescale. What about other forms of nuclear propulsion? There exists a concept called nuclear electric propulsion. In this scheme, a nuclear reactor produces electricity, which then powers an ion drive, or a similar electric thruster. Ion drives work by accelerating ions, which are simply charged particles, to extraordinary speeds and ejecting them out the rear of the spacecraft. The thrust at any instant is laughably small. You could not feel it pushing you, but it's relentless and continuous, and over long stretches of time, you can build up genuinely impressive cumulative speeds. NASA's Dawn spacecraft, which explored the asteroid Vesta and the dwarf planet Ceres, used ion propulsion. It ran on solar panels rather than a nuclear reactor, but the principle is identical. Dawn racked up a total change in velocity of roughly 25,000 miles per hour over the course of its mission. That's an impressive figure given its size and power budget, but it remains far too sluggish for any kind of interstellar trip. Even outfitted with a much more powerful nuclear reactor providing significantly more energy, nuclear electric propulsion would probably top out at roughly 1 or 2% of the speed of light at best. At 1% the speed of light, traversing a single light year requires about 100 years. That's longer than any human lifetime by a comfortable margin. You'd need multiple generations on board. A crew would depart Earth fully aware that their grandchildren would be the ones who actually arrived. This is the concept of a generation ship, and it dredges up a parade of difficult questions. How do you sustain a closed ecosystem for 100 straight years? How do you keep the ship from gradually breaking down across centuries of use? How do you preserve social cohesion when everyone aboard knows they will die before reaching the destination? How do you prevent genetic problems from emerging in such a tiny, isolated population? These aren't impossible problems. They might even be solvable in principle. But they're genuinely difficult, and we haven't begun to crack them. So nuclear electric propulsion might get us to 1% of light speed, maybe 2% if we're truly optimistic. That still means 50 to 100 years to cross a single light year. What about fusion? Nuclear fusion is the process powering the sun itself. It involves slamming hydrogen nuclei together under unimaginable temperatures and pressures until they merge into helium, releasing tremendous amounts of energy in the process. We've been chasing practical fusion reactors on Earth for decades. We've achieved fusion in laboratories. We've even crossed the threshold of net energy gain, where a fusion reaction releases more energy than was needed to ignite it. But we still don't have a single working fusion power plant feeding electricity to a city. The engineering challenges are profound. You have to confine plasma at temperatures measured in millions of degrees, hotter than the core of the sun itself. You have to maintain that confinement long enough for fusion reactions to produce usable energy. You have to extract that energy efficiently without destroying the equipment around it. It's brutally difficult, and the work continues. But suppose we crack it. Could fusion be harnessed for spacecraft propulsion? In theory, yes. A fusion rocket would heat propellant to extreme temperatures, using fusion reactions, and shoot that propellant out the back at tremendous velocity. If you could continuously accelerate at a reasonable rate using fusion power, you might be able to reach somewhere between 10 and 20% of light speed. At those speeds, you're looking at 5 to 10 years to cross a single light year. Now that begins to feel almost practical. 5 years is a long time, certainly, but it's well within the range of what humans have already pulled off in space. Astronauts have spent over a year aboard the International Space Station on a single tour. 5 years would be brutally challenging, but not categorically impossible. But here's the painful reality. We don't have fusion propulsion. We don't even have fusion power plants on Earth yet, much less compact ones, small enough to bolt onto a spacecraft. Building a fusion rocket capable of accelerating to 10 or 20% of light speed would require solving every problem of fusion power on Earth, plus a host of additional problems involving miniaturization, radiation shielding, propellant storage, and entire spacecraft architecture. It's almost certainly decades away at the absolute minimum, possibly centuries. So fusion propulsion is theoretically achievable, but practically we are nowhere near it. Now let's wade into the more speculative waters. What if we could somehow travel at a serious fraction of light speed? Not 5 or 10 or 20%, but 50 or even 90%? Various proposals have been put forward. Antimatter propulsion is one of them. When matter and antimatter come into contact, they annihilate each other completely, converting all of their mass into pure energy, according to Einstein's famous equation, E equals mc squared. This is, hands down, the most efficient energy conversion process we know of. A single kilogram of antimatter annihilating with a kilogram of regular matter would release roughly 180 times more energy than a kilogram of hydrogen undergoing fusion. If you could somehow harness this energy and channel it into propulsion, you could in principle achieve genuinely high velocities. Some estimates suggest that antimatter rockets could reach as much as 70 or 80% of light speed. At those speeds, you'd cover a single light year in roughly 15 to 17 months. This is fast. This is genuinely fast. You could reach Proxima Centauri in about 5 or 6 years. You could reach stars dozens of light years away within a single human lifetime. But there's a problem, actually several problems. First, we cannot produce antimatter in any meaningful quantity. Antimatter can be created in particle accelerators, but only in vanishingly tiny amounts. CERN's accelerators churn out roughly 1/1000th of a gram of antimatter per year. At that rate, producing a single gram would take somewhere around 100 billion years. That's longer than the current age of the universe, several times over. Second, storing antimatter is fiendishly difficult. Antimatter annihilates the instant it touches normal matter. You can't simply pour it into a tank. You have to suspend it in a perfect vacuum using carefully tuned magnetic fields, never letting it brush against the walls of its container. We can do this for individual particles or small clusters in research labs. Scaling that up to the kilograms or tons you'd need for a serious spacecraft is fantastically beyond anything we currently know how to do. Third, the energy released from matter-antimatter annihilation is notoriously difficult to capture efficiently. A large fraction comes out as gamma rays and neutrinos, both of which are extraordinarily hard to catch and direct for thrust. You would only be able to use a fraction of the available energy effectively. Fourth, even assuming you solved every preceding problem, the spacecraft itself would require massive shielding to protect any crew from radiation. At high fractions of light speed, even tiny dust particles drifting in interstellar space become catastrophically dangerous. A single grain of sand striking your hull at 80% of light speed would release energy comparable to a substantial bomb. You would need meters of shielding, which adds mass, which demands more fuel, which adds more mass. Still, it's a vicious feedback loop. So antimatter propulsion is theoretically possible, but practically remains pure science fiction. We are not close to building it, and it's entirely possible we never will be. What about concepts that don't require carrying any fuel at all? There's an idea called a laser sail, sometimes called a light sail. The basic concept is elegant. You construct a spacecraft equipped with a large, paper-thin, reflective sail. You aim a tremendously powerful laser from Earth onto that sail. The photons from the laser bounce off the surface and transfer momentum to the spacecraft, pushing it forward. Because you're not carrying any fuel on board, the spacecraft itself can be incredibly light, which means even a small amount of momentum transfer can produce significant acceleration. There's a project actively exploring this idea called Breakthrough Starshot. The plan is to launch thousands of tiny spacecraft, each weighing only a gram or two, each equipped with a light sail spanning a few meters. Ground-based laser arrays would hammer those sails with such intense beams that the probes would be accelerated to roughly 20% of light speed in a matter of minutes. At 20% the speed of light, they would reach Proxima Centauri in around 20 years. They would scream past the system, snapping pictures and gathering measurements, then beam the data back to Earth. The data transmission itself would take another 4 years to crawl back to us. So the total mission from launch to receiving the first photographs of another star system would clock in around 24 years. This is genuinely exciting. It's theoretically achievable using technology not too far beyond our current capabilities. But it carries significant challenges. The lasers would have to be staggeringly powerful, combining the output of countless individual laser units to forge a single beam strong enough to push the probes. The aiming would need to be flawless, tracking objects accelerating away from Earth at relativistic speeds. The sails themselves would have to be impossibly light and impossibly reflective. The spacecraft would need to survive the brutal acceleration phase without disintegrating. Even setting all those challenges aside, the breakthrough Starshot probes would be tiny flyby missions. They cannot stop, they cannot enter orbit, they cannot land. They cannot send humans. They are, in essence, microchip-sized cameras hurled through another star system at roughly 60 million miles per hour, snapping a few quick frames before continuing forever into the dark on the other side. And even with everything working perfectly and the probes reaching 20% of light speed, traversing a single light year still requires 5 years. And that's assuming nothing goes wrong. So let's pull back and look at what we've gathered. Using our current fastest spacecraft, the Parker Solar Probe, traveling a single light year would take about 1,560 years. With the Voyager probes, it would take about 17,600 years. With theoretical nuclear pulse propulsion in the style of Project Orion, perhaps 20 years. But we are not building it. With nuclear electric propulsion, perhaps 50 to 100 years, but the technology doesn't exist yet. With fusion propulsion, perhaps 5 to 10 years, but fusion drives don't exist either. With antimatter propulsion, perhaps 1 to 2 years, but antimatter production and storage are leagues beyond our capabilities. With laser sails, perhaps 5 years for a tiny gram-scale probe. But even that technology remains experimental. The reality is sobering. We cannot travel to the stars with any current technology. We can barely even leak out of our own solar system. Voyager 1, after 45 years of continuous flight, has covered only about 2/1000ths of a single light year. To complete a full light year at Voyager's pace would require 17,600 years. The stars are so impossibly far that even light, the fastest thing in the entire universe, takes years to travel between them. And we are so painfully slow compared to light that the journey becomes almost meaningless to think about. 1 light year might as well be infinity. We can't traverse it in any practical sense. Not within a human lifetime, not within many human lifetimes stacked end to end. The astronomer Carl Sagan once famously said that the cosmos is all that is, or ever was, or ever will be. But for us, for humanity as we currently exist, the cosmos might as well end at the edge of our solar system. The stars beyond are beautiful to gaze at. They're fascinating to study from a distance. But they are not destinations we can visit. They are just lights pinned in the dark, forever beyond our reach. This is the harsh truth of the universe we inhabit. The distances between stars are so vast that they are functionally impossible with anything resembling current technology. Even with optimistic projections about future capabilities, traveling a single light year would take years at minimum, possibly decades or centuries. Now, this doesn't mean interstellar travel is forever locked away from us. Technology advances. We went from the Wright brothers' first powered flight in 1903 to humans walking on the moon in 1969. That's only 66 years, from the first airplane to footprints on another world. Maybe in another century or two we'll have fusion drives or antimatter engines or something that hasn't even occurred to anyone yet. Maybe we'll figure out how to construct generation ships capable of supporting human populations across thousands of years. Maybe we'll develop artificial intelligences that don't require life support and can travel for millions of years without complaint. Maybe we'll uncover new physics that permits faster than light travel, though that seems exceedingly unlikely given everything we currently understand. But with what we have right now, with what we'll have in the foreseeable future, the stars remain genuinely out of reach. 1 light year is an impossible distance, and the closest star is more than 4 light years away. Let me give you one more way of feeling this in your bones. The fastest speed any human being has ever traveled was during the Apollo 10 mission in 1969. The command module reached around 24,791 miles per hour during re-entry. That's roughly 6.89 miles per second. At that speed, traveling a single light year would take roughly 27,000 years. The astronauts aboard Apollo 10 hold the record for the fastest humans in history, and even with that title, they would still need 27,000 years to cover a single light year. 27,000 years ago, the ancestors of modern humans hadn't fully emerged from the late stages of the last ice age. Cities did not exist. Agriculture had not yet been invented. The entire span from the late Paleolithic to today, with all of its glacial epochs, all of its evolutionary adjustments, all the slow grinding of geological time, would need to elapse, and you still wouldn't have arrived. This is the scale we're dealing with. This is why 1 light year might as well be infinite. Some people find this idea genuinely depressing. The notion that we are confined to our little solar system, that the stars are forever out of reach, that the universe is so vast and we are so unbearably slow. But there's another way to hold this thought. Our solar system is actually quite enormous. Earth is small, yes, but the solar system stretches far beyond the planets. The Kuiper Belt, where Pluto orbits, reaches out to about 4 billion miles from the Sun. Beyond that lies the scattered disk, extending out to roughly 9 billion miles. Beyond even that lies the Oort cloud, a vast spherical shell of icy bodies that may extend out to a full light year from the Sun, perhaps even 2. The Oort cloud is still gravitationally bound to our Sun, still part of our solar system, so our solar system might actually be about 2 light years across, end to end. That's a tremendous amount of space. There could be millions or even billions of objects scattered throughout the Oort cloud. We've barely begun to explore the outer solar system. We've sent probes to the planets, yes. We've studied Jupiter and Saturn and their varied moons. We've flown past Pluto. But the overwhelming majority of the solar system remains entirely unexplored. There could be undiscovered dwarf planets out there. There could be peculiar objects with strange orbits. There could be resources we haven't even conceived of yet. Maybe instead of dreaming about reaching other stars, we should focus on thoroughly exploring and developing our own solar system. There may be enough here to keep humanity occupied for thousands of years. We could build habitats on asteroids. We could mine the moons of Jupiter and Saturn for water and metals. We could establish research outposts throughout the outer solar system. We could study the Oort cloud and the Kuiper Belt in detail. We could create a civilization that spans the solar system, with billions of people living in space habitats, on terraformed moons, on artificial worlds carved out of asteroid material. And maybe centuries from now, after we've fully developed our solar system, after we've matured our technology, we'll be ready to take the next step. We'll build generation ships powered by fusion or antimatter. We'll send them toward nearby stars, knowing the journey will swallow decades or even centuries. And humanity will slowly, patiently spread to other star systems, one at a time, over thousands or even millions of years. But that's a long way off. For now, for our own lifetimes, for our children's lifetimes, probably for our grandchildren's lifetimes, we are confined to this solar system. And when you ask how long it would take to travel 1 light year, the honest answer is too long. Far too long for any practical purpose with current technology. Too long for a single human life. Too long for many human lives stitched together. The universe is vast, and we are slow. The stars are distant, and 1 light year might as well be forever. But we're here. We're on Earth, orbiting our sun in our solar system, and maybe that's enough. Maybe for now, home is enough. Let me leave you with one final thought before we keep digging. The speed of light is often called the cosmic speed limit. According to our current understanding of physics, nothing with mass can travel faster than light. And light, by definition, takes 1 year to travel 1 light year. If we could somehow travel at the speed of light, which we genuinely cannot because anything possessing mass would require infinite energy to reach that velocity, but if we could, traveling 1 light year would take exactly 1 year. But here's something strange. From the perspective of the traveler, time dilation effects would mean the journey appears even shorter than that. At 99% of light speed, time slows substantially. A trip that takes 10 years from Earth's perspective would feel like only about 1.4 years to the traveler aboard the spacecraft. At 99.9% of light speed, that 10-year journey would feel like roughly 5 months. At 99.99% of light speed, it would feel like roughly 2 weeks. And at exactly the speed of light, if it were somehow attainable, no time would pass at all from the traveler's frame of reference. From a photon's point of view, a journey from one side of the universe to the other is instantaneous. Of course, we cannot reach the speed of light. We probably cannot even reach 99% of it. The energy requirements are absurd, and the engineering challenges feel insurmountable when measured against anything we can realistically imagine constructing. But it's intriguing to think about. The universe imposes hard limits on how fast we can travel, And those limits make the stars unreachable with current technology. They might make the stars unreachable forever. Or they might just mean we need to be patient, slowly developing our technology over centuries or millennia until we are finally ready. Either way, the answer to how long it would take to travel 1 light year is clear. With what we have now, it would take over 1,000 years. With optimistic projections of future technology, it might take decades or centuries. With technology that might never exist, it could take years or even months. But the stars remain distant. 1 light year remains an essentially infinite distance. And for now, we remain here on this small blue world, looking up at lights we can see but cannot touch. The universe is beautiful. The stars are magnificent. But they are far, far away, so far that 1 light year might as well be the edge of reality itself. Thanks for sticking with me through this part of the journey. The question was simple, but the answer has revealed something profound about our place in the cosmos. We are bound to our solar system by the staggering distances of space and the immutable laws of physics. The stars are right there. We can see them, we can study them, but we cannot reach them. Not yet. Maybe not ever. And in that limitation, there's both humility and wonder. Humility because we are reminded of how small and how slow we truly are. Wonder because the universe is so vast and so dense with places we can imagine but never visit, at least not in our lifetimes. 1 light year, a simple unit of distance. But crossing it would take longer than human civilization has existed. And that's the reality we live with. That's the cage of distance and time that binds us to this corner of space. And maybe that's okay. Maybe being here on Earth, in this solar system, is enough. Because home isn't measured in light years. Home is measured in moments, in the people and places that matter to us. And our home, this solar system, this Earth, is right here, not 1 light year away, not millions of years of travel away. Right here. And sometimes right here is exactly where we need to be. But let's dig deeper into why this distance is so impossible. Let's examine the physics that make 1 light year such an insurmountable barrier. It's not merely a question of building a faster engine. It's about fundamental limitations woven into the very fabric of reality itself. When we talk about traveling close to the speed of light, we are not just discussing engineering puzzles. We're confronting energy requirements that absolutely shatter intuition. Einstein's theory of special relativity tells us that as you approach the speed of light, your effective mass increases. The closer you push to light speed, the more energy is required to accelerate you any further. At 90% of light speed, your effective mass is about 2.3 times your rest mass. At 99%, it climbs to roughly 7 times your rest mass. At 99.9%, it balloons to around 22 times your rest mass. And at exactly the speed of light, your effective mass becomes infinite. This means the energy needed to accelerate you to light speed also becomes infinite. It's not merely a practical impossibility. It's a fundamental impossibility, according to the laws of physics as we currently understand them. You cannot reach the speed of light if you possess mass. Only massless particles like photons can travel at light speed, and they always travel at light speed. They cannot move slower. They cannot move faster. From the moment they are created until the moment they are absorbed, they move at exactly that universal velocity. So if we cannot reach light speed, what's the maximum velocity we could theoretically achieve? Let's think about it in terms of energy. The kinetic energy of an object in classical physics is half its mass times velocity squared. Double the speed, and you need 4 times the energy. Triple it, and you need 9 times. But that formula breaks down as you push toward the speed of light. At relativistic speeds, the energy demands grow far faster than the classical equation predicts. Accelerating 1 kilogram to 10% of light speed requires roughly 4.5 times 10 to the 14th joules. That's about the energy locked in 10,000 kilograms of gasoline. Accelerating 1 kilogram to 50% of light speed requires about 1.3 times 10 to the 16th joules, equivalent to roughly 300,000 kilograms of gasoline. Accelerating 1 kilogram to 90% of light speed requires about 1.2 times 10 to the 17th joules, equivalent to about 2.8 million kilograms of gasoline. Notice how the energy requirements outpace the speed itself. Going from 10% to 50% of light speed multiplies the velocity by 5, but the energy requirement leaps by about 29 times. Going from 50% to 90% multiplies the speed by 1.8, while the energy demand jumps by about 9 times. This is the tyranny of the rocket equation tangled up with relativistic effects, and it actually gets worse, because these calculations assume 100% efficiency in converting fuel to kinetic energy. In reality, no engine is 100% efficient. Chemical rockets are roughly 3 to 4% efficient. Ion drives perform better, somewhere around 50 to 70%. Nuclear fusion, if we ever build it, might land at 70 to 80% efficient. Matter-antimatter annihilation could theoretically reach about 90% efficiency if you could capture all the released energy. But even with perfect efficiency, the energy demands remain staggering. A spacecraft weighing 1,000 kilograms, roughly the mass of a small car, would require about 1.3 times 10 to the 19th joules to reach 50% of light speed. That's roughly the entire annual output of a large nuclear power plant. Every joule of that energy would have to be either stored on the spacecraft or generated somehow during the journey. If you're using fusion, you have to carry fusion fuel. Hydrogen is the lightest option, but you'd still need tons of it. And remember, the more fuel you load up, the more mass you have, which means you need even more fuel to accelerate that additional mass. The rocket equation is brutal. Every kilogram of payload demands multiple kilograms of fuel. Every kilogram of fuel is additional mass that itself must also be accelerated. This is why conventional rockets can never carry us to high fractions of light speed. The fuel requirements grow exponentially. By the time you've added enough fuel to reach genuinely high velocities, your spacecraft is mostly fuel tanks, and you've slammed into a wall of diminishing returns. This is precisely why ideas like laser sails are attractive. If you don't have to carry your fuel at all, if the energy comes from an external source like a laser beam fired from Earth, you sidestep the rocket equation entirely. But laser sails carry their own difficulties. The laser must be tremendously powerful and surgically aimed. The sail must be enormous and impossibly lightweight. And once you've accelerated, you cannot slow down, unless you have a second laser at your destination, which obviously you don't, because you haven't gotten there yet. So laser sails are wonderful for flyby missions, where you're simply blasting through a star system snapping pictures, but they are useless for any mission that involves arriving and staying. What about more exotic concepts? What about warp drives? You may have heard of them from Star Trek and other science fiction. The idea is that instead of moving the spacecraft through space, you bend space itself around the spacecraft, contracting space in front of you and expanding it behind you. Within this warp bubble, you experience normal physics, but the bubble itself moves through space, potentially faster than light. The Mexican physicist Miguel Alcubierre proposed a mathematical solution to Einstein's field equations in 1994 that described exactly this kind of bubble. The Alcubierre drive, as it's now called, is genuinely allowed by general relativity. It doesn't break the rules. Inside the bubble, the spacecraft never exceeds light speed in its local frame, so it doesn't violate special relativity. But the bubble itself can move faster than light, because space itself can expand and contract faster than light. It's brilliant, it's elegant, and it almost certainly doesn't work in any practical sense. The first problem is that creating such a bubble would require exotic matter with negative mass and negative energy density. We have never observed anything with negative mass anywhere in the universe. Some quantum effects produce minuscule amounts of negative energy density, like the Casimir effect, but nowhere near the quantities required to construct a warp bubble. We have absolutely no idea how to manufacture exotic matter in the necessary amounts. The second problem is that the energy requirements are utterly absurd. Early calculations suggested you'd need the mass-energy equivalent of the entire observable universe to build a warp bubble large enough for a small spacecraft. Later refinements brought the figure down to the mass energy of Jupiter, which is still impossible, but at least no longer ridiculous. More recent work has shaved the requirement further, but we are still talking about energy levels far beyond anything we can generate or even imagine generating. The third problem is that you would have no way to steer the bubble once you were inside it. The front of the bubble is moving faster than light, which means you cannot send signals to it from inside. You'd have to set your course before activating the warp drive, and simply hope you'd aimed correctly. The fourth problem is that as you traveled, you would accumulate particles and radiation on the leading edge of the bubble, When you eventually deactivated the bubble, all of that accumulated energy would be released in a cataclysmic burst that would likely vaporize whatever you'd been trying to reach. Showing up at your destination with the equivalent of a planet-killing weapon strapped to your front bumper is not a great way to introduce yourself. So warp drives remain firmly in the territory of science fiction. They are not strictly impossible according to our current physics, but they require technology and energy sources that might as well be magic. What about wormholes? Within general relativity, it's mathematically possible for spacetime to be connected in unusual ways. You could have a shortcut threading through the fabric of spacetime, a wormhole linking two distant points. Travel through the wormhole, and you could in principle cross vast distances instantaneously, or near enough to it. Einstein and Nathan Rosen first proposed this idea in 1935. Einstein-Rosen bridges, as they are sometimes called, are valid solutions to Einstein's field equations. They are mathematically permitted, but the practical problems are severe. First, naturally occurring wormholes, if they exist at all, would be microscopic, far too small for anything macroscopic like a spacecraft to pass through. To create a traversable wormhole, one large enough and stable enough to send something through, you'd once again need exotic matter, specifically matter possessing negative energy density, which is required to hold the wormhole's throat open. Without it, the wormhole would collapse the moment you tried to use it. Second, even if you could create a wormhole, you'd need to get one end of it to your destination. If you wanted a wormhole running from Earth to Proxima Centauri, you would have to physically transport one mouth of the wormhole across the gap to Proxima Centauri at less than light speed. Once it arrived, you'd have your shortcut, but creating the shortcut would take just as long as conventional travel. So wormholes don't really help with the initial exploration of space. They might be useful for maintaining connections between already established colonies in the very distant future, but they don't solve the fundamental problem of getting somewhere in the first place. Let's come back to more grounded ideas. What if we accepted the slowness? What if we embraced the fact that interstellar travel will take thousands or even millions of years, and designed our missions around that reality? This brings us to the concept of generation ships. A generation ship is a spacecraft engineered to support multiple successive generations of humans across centuries or millennia. The idea is that the original crew who depart Earth will not live to see the destination. Neither will their children or their grandchildren. Multiple generations will be born aboard, live their entire lives within the metal walls of the ship, and die there. Eventually, after many generations, their descendants will arrive at the destination. The original mission belonged to people now long dead. This concept raises a tangled web of questions. How do you maintain a closed ecosystem for thousands of years? Plants generate oxygen and food, but they require water, nutrients, and light. You'd have to recycle absolutely everything with near-perfect efficiency. Every drop of water, every nutrient, every atom of carbon would need to be recovered and reused. We have done this on a tiny scale on the International Space Station, but never for prolonged periods with complete recycling. Losses are inevitable. Some atoms will be incorporated into structures and never recoverable. Some will leak out through airlocks. Across centuries, those small losses accumulate into deficits that could doom the mission. You would need massive redundancy and reserves to absorb those losses. How do you maintain genetic diversity in a small, isolated population? A generation ship might carry a crew of hundreds, or perhaps a few thousand. That's a tiny gene pool by any measure. Across multiple generations, you would see inbreeding, genetic drift, and the gradual accumulation of harmful mutations. This is a serious problem we already observe in endangered species. When a population drops below a certain threshold, genetic problems begin to surface. You would need to carefully manage reproduction, possibly using stored genetic material or even genetic engineering to maintain healthy diversity across generations. How do you maintain social cohesion? Everyone aboard the ship is traveling toward a destination they personally will never see. They are spending their entire lives in a confined space for the benefit of distant descendants. What keeps them motivated? What prevents social breakdown, internal conflict, or even outright mutiny? You would need strong cultural traditions, a sense of shared purpose, perhaps even religious or philosophical frameworks to give meaning to the journey, and you'd need to preserve knowledge and skills across generations. The people who finally arrive at the destination need to know how to build a colony, how to survive on a new world. They cannot simply be passengers. They need to be engineers, scientists, farmers, builders, doctors, leaders. How do you prevent technological failure? Machines break down, components wear out. Across centuries, every system aboard the ship will fail multiple times. You would need spare parts, manufacturing facilities, repair expertise. You would need to train each generation in the skills required to maintain the vessel. If a critical system fails and there is no one alive who knows how to repair it, the mission ends. All of these challenges are solvable in principle, but they are formidable. And we have never tested any of this. We have never had a closed ecosystem that has been completely self-sufficient for more than a handful of years. We have never had a small population isolated for multiple generations. We don't know if it would work. We don't know what unforeseen problems would emerge. But let's assume we solve everything. Let's assume we build a generation ship that functions perfectly. How long would it take to travel 1 light-year aboard such a ship? Well, that depends on how fast the ship can move. If we use nuclear pulse propulsion or fusion drives, perhaps we could reach 5 to 10% of light speed. At 5%, traveling 1 light-year takes 20 years. That's less than a single generation, so at that point it isn't really a generation ship at all. At 1% of light speed, which is more realistic with nuclear electric propulsion, traveling 1 light-year takes 100 years. That's 3 to 4 generations depending on how you count them. The great-grandchildren of the original crew would be the ones to arrive. At 0.1% of light speed, which is achievable with advanced ion drives, traveling 1 light-year takes 1,000 years. That's about 30 to 40 generations. Nobody alive at the destination would have any living connection to the people who departed Earth. The departure would be ancient history, passed down through stories and historical records. At 0.01% of light speed, traveling 1 light-year takes 10,000 years. That's about 300 to 400 generations. Entire civilizations have risen and fallen on Earth in 10,000 years. The crew arriving at the destination would be so far removed from the crew that left Earth that they might not even remember why they were on the ship. The mission could have devolved into mythology, a story about a beginning of time when their ancestors departed a place called Earth, half remembered, half invented. This actually raises a profound philosophical question. If a generation ship travels for 10,000 years, is it still the same mission? The people who arrive have no direct connection to the people who left. They have lived their entire civilization aboard the ship. In what sense are they still carrying out a mission planned by people who lived 300 generations ago? Do they even still want to colonize a planet? Maybe they have adapted entirely to life on the ship. Maybe they have built a functioning society in space and have no interest in disembarking. Maybe the idea of living on a planetary surface, exposed to weather, gravity, and the unfiltered sky, seems strange and unnatural to them, even repulsive. This is one of the strange implications of very long generation ship journeys. The mission could evolve, change, or even be abandoned by descendants whose values and desires are wildly different from those of the original planners. The destination becomes secondary. The voyage itself becomes the point. Now let's think about time dilation again, more deeply this time. One of the strangest effects of special relativity is that time passes differently for objects moving at different speeds. If you are traveling at a significant fraction of the speed of light, time passes more slowly for you than it does for people who are stationary. This is time dilation, and it has been confirmed experimentally many times. We've sent atomic clocks aboard fast-moving aircraft and measured that they tick slightly slower than identical clocks remaining on the ground. GPS satellites have to actively account for time dilation because they are moving fast relative to Earth's surface, and without those corrections, your phone's navigation would drift miles off course within hours. At everyday speeds, the effect is vanishingly small, but at speeds close to the speed of light, time dilation becomes dramatic. At 50% of light speed, time passes about 87% as fast for the traveler compared to someone stationary. A 10-year journey from Earth's perspective would feel like 8.7 years to the traveler. At 90% of light speed, time passes about 44% as fast. A 10-year journey would feel like 4.4 years. At 99% of light speed, time passes about 14% as fast. A 10-year journey would feel like 1.4 years. At 99.9%, time passes about 4.5% as fast. A 10-year journey would feel like roughly 5.4 months. So if you could somehow travel at 99.9% of light speed, a journey of 1 light year would take about a year from Earth's perspective, but only about 16 days from your own perspective inside the ship. You would have aged 16 days while everyone on Earth aged a full year. If you traveled to Proxima Centauri and back, a round trip taking 8.5 years from Earth's frame, you would only age about 136 days, less than 5 months. But everyone you knew on Earth would be 8.5 years older. If you went to a star 100 light years away and returned, 200 years would pass on Earth, but you might only age a few years personally. You would step off the ship into an Earth where everyone you had known was long dead, where the world had transformed beyond recognition. This is the twin paradox, one of the most famous thought experiments in special relativity. If you have identical twins and one stays on Earth while the other travels at near light speed to a distant star and back, the traveling twin will be younger when they reunite. It isn't an illusion. Time really does pass more slowly for the traveling twin. They really do age less. Their cells really do divide fewer times. They really do experience less subjective duration. So time dilation offers a way for individual travelers to make long journeys without personally experiencing the full duration. But it doesn't solve the energy problem. You still need enormous energy to accelerate to 99% of light speed. And it doesn't help the people left behind. While you're zipping across the galaxy, aging only a few years, centuries are passing on Earth. If you ever wanted to come home, you would be returning to a world that had moved on without you. Everyone you knew would be dead. Your entire society might have transformed completely or even collapsed entirely. You would be a time traveler stranded in the future, unable to return to the era you remembered. This has profound implications for any realistic interstellar travel. Even if we develop the technology to travel at high fractions of light speed, even if time dilation makes the journey short from the traveler's perspective, the journey is still impossibly long from the perspective of human civilization as a whole. Send a ship to a star 100 light years away, and a century will pass before anyone on Earth even knows whether it arrived safely. Another century will pass before any data comes back. That's 200 years total, 8 to 10 generations. Nobody alive when the ship returns will personally remember the people who left. This makes it extraordinarily difficult to maintain continuity across interstellar distances. You cannot have a unified human civilization spanning many star systems if it takes centuries for information to crawl between them. Each colony would effectively be independent, isolated by the vast distances and the finite speed of light. Over time, colonies would diverge. They would develop their own cultures, their own languages, perhaps even their own subspecies, as they adapt to different environments. A colony on a high-gravity world might evolve to be shorter and more robustly built. A colony in low gravity might become taller and more delicate. Given enough time, thousands or millions of years, colonies might diverge so dramatically that they would no longer even be the same species. This is speculative, of course. We don't know how quickly human evolution would proceed in different environments, especially if we're employing genetic engineering or other technologies. But the central point stands. Interstellar colonization, even if successful, would not produce a unified human empire like the ones depicted in science fiction. It would produce isolated pockets of humanity, each developing independently, connected only by faint signals taking decades or centuries to travel between them. Now let's talk about the practical economics of interstellar travel. Even if we could build a ship capable of reaching another star, who would actually pay for it? The cost would be astronomical, to use the painfully appropriate word. Building a fusion-powered generation ship capable of carrying thousands of people would cost trillions of dollars, possibly tens or hundreds of trillions. It would require decades of construction, massive industrial infrastructure in space, and the dedication of an enormous fraction of humanity's resources for an extended period. What's the return on investment? If you send a colony ship to another star system, and it takes thousands of years to get there, you will not see any benefit in your lifetime. Neither will your children, neither will your grandchildren. The colony might eventually send back information, but that data will take hundreds or thousands of years to reach Earth. There is no possibility of trade across interstellar distances. You cannot ship goods between stars, because the journey takes too long. By the time your cargo arrives, it is obsolete by centuries. Information can be transmitted at the speed of light, which is faster than any ship, but even that takes years or decades. A conversation with a colony 100 light years away would take 200 years for a single exchange of messages. You send a message. A century later, they receive it. They send a reply. A century after that, you receive their reply. Nothing about that timeline supports anything resembling a functioning economy. So the economic motivations for interstellar travel are extraordinarily weak. There is no realistic profit to be made. Any colony you establish will be effectively independent within a few generations. The only motivations are non-economic. Survival, ensuring that humanity isn't confined to a single planet that could be destroyed by an asteroid or some other catastrophe. Curiosity, the drive to know what's out there. Adventure, the same impulse that drove our ancestors out of Africa. Religious or ideological commitments, the desire to plant the flag of a particular belief system on another world. These are powerful motivations for some people, but they don't fit neatly into normal economic decision-making. They require a society willing to commit enormous resources to projects that won't yield any tangible benefits within many lifetimes. So when you ask how long it would take to travel 1 light year, the technical answer depends on the technology. With current technology, over 1,000 years. With near-future technology, perhaps decades to centuries. With far-future technology, perhaps years. But the real answer is that we are not traveling 1 light year anytime soon. Not because we cannot in principle, but because we have not solved all the prerequisite problems. We have not built the infrastructure. We have not developed the technology. We have not committed the resources. And maybe we never will. Maybe interstellar travel will remain forever beyond our reach. Not because it's physically impossible, but because it's impractical. Maybe humanity's future lies entirely within this solar system. Building habitats, terraforming moons, creating a civilization that spans the planets but never escapes the sun's gravitational embrace. There is nothing wrong with that. The solar system is vast. There's room for trillions of people if we build habitats in space. There are resources sufficient to sustain a civilization for millions of years. We could have a rich, diverse, thriving civilization without ever leaving the solar system. Or maybe thousands of years from now, we will look back at this era and laugh at how limited our thinking was. Maybe we will have technologies we cannot even imagine today. Maybe we will have solved the energy problem, the propulsion problem, the life support problem. Maybe we will have colonies around hundreds of stars. Maybe humanity will spread across the galaxy over millions of years, slowly but steadily expanding our reach. But that is speculation. That is hope for a distant future. For now, for us, 1 light year remains an impossible distance. Let me give you yet another way to think about this. Imagine you could convert matter directly into energy with 100% efficiency. This is essentially what happens during matter-antimatter annihilation. Every kilogram of matter contains a tremendous amount of latent energy, according to Einstein's equation, E equals mc squared. 1 kilogram of matter, fully converted to energy, produces about 9 times 10 to the 16th joules. That is roughly the energy of 21.5 megatons of TNT. It's roughly the energy released by the largest nuclear weapons ever tested, packed into a single kilogram. Now let's say you want to accelerate a spacecraft to 50% of light speed, and then decelerate it when you reach your destination. You need energy to speed up and energy to slow down. For a spacecraft with a payload of 1,000 kilograms, you'd need about 2.6 times 10 to the 19th joules. Using matter-antimatter annihilation with 100% efficiency, you'd need about 290 kilograms of fuel, 145 kilograms of matter, and 145 kilograms of antimatter. That isn't actually that much in absolute terms. A few hundred kilograms is, in principle, manageable. But remember, we cannot produce antimatter in any meaningful quantity. The total amount of antimatter ever produced by humans is less than 20 nanograms. That's 20 billionths of a gram. To produce 145 kilograms of antimatter at our current rate would take about 300 trillion years. That's about 22,000 times the current age of the universe. So even with perfect energy conversion, we are limited by our inability to produce or store antimatter in any practical quantity. And this assumes 100% efficiency in converting energy to thrust, which is also impossible. Real engines have losses: heat, radiation, inefficiencies in every step of the energy conversion process. You would probably need several times more fuel to account for these realistic losses. The point is that even in the most optimistic scenarios, employing technologies that are theoretically possible but practically impossible, traveling 1 light-year remains enormously difficult. It demands energy levels and technologies far beyond anything we have today. And 1 light-year is just the beginning. The nearest star is 4.24 light-years away. Most stars are dozens, hundreds, or thousands of light-years away. The Milky Way galaxy is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The observable universe is 93 billion light-years across. 1 light-year is tiny on cosmic scales. It's the smallest meaningful unit of interstellar distance. And yet it's vast beyond our ability to cross with any technology we can currently imagine building. This is the fundamental reality of living in this universe. The speed of light is finite. Distances are immense. Energy is limited. We are slow and small and bound to this corner of space by physics itself. You can rage against it. You can dream about warp drives and wormholes and clever ways to cheat the laws of physics. But until someone discovers genuinely new physics, until someone finds a loophole in relativity that we have not detected in over a century of testing, we are stuck with these limitations. The stars are beautiful. They are fascinating. They are full of wonders we would love to explore, but they are far away. So far away that 1 light-year, the smallest step toward them, might as well be infinite. And yet, knowing all this, understanding our limitations, there is still something wonderful about looking up at the night sky. Because even though we cannot reach the stars, we can see them, we can study them, we can learn about them, we can understand how they work, what they're made of, how they live and how they die. We can detect planets orbiting other stars. We can search for signs of life. We can wonder if, somewhere out there around some distant star, someone else is looking up at their own night sky and wondering the same things we are. The distance might separate us forever, but the questions, the curiosity, the wonder, those are universal. And maybe that's enough. Maybe the journey isn't about physically reaching other stars. Maybe it's about expanding our understanding, pushing the frontiers of knowledge, learning everything we can about this vast universe we find ourselves inside. We may never leave this solar system, but our knowledge, our understanding, our curiosity can reach across light years. Our telescopes can see galaxies billions of light years away. Our mathematics can describe the birth of the universe and the eventual death of stars. Our minds can grasp concepts that span time and space in ways our bodies never will. And in that sense, we have already traveled farther than any spacecraft ever could. We have already crossed distances that would take light billions of years to traverse. We have already explored the universe in the only way that really matters, through understanding. So when someone asks how long it would take to travel 1 light-year, the answer is layered. Physically, with current technology, over 1,000 years. With future technology, perhaps decades or centuries. With impossible technology, perhaps years or months. But intellectually, we have already made that journey. We have already crossed that distance in our minds, in our mathematics, in our understanding of the cosmos. And that journey, the journey of discovery and understanding, never ends. There is always more to learn, always more to discover, always more questions to ask. The physical journey to the stars might be impossible, but the intellectual journey has no limits. And in the end, maybe that's the journey that matters most. Let's talk about some specific historical attempts to think seriously about interstellar travel, because humans have been dreaming about reaching the stars for far longer than you might think. In 1973, the British Interplanetary Society started a project called Project Daedalus. The aim was to design an unmanned interstellar probe capable of reaching Barnard's star, a star about 6 light-years away, within a single human lifetime. The design they came up with was ambitious almost to the point of audacity. The spacecraft would use a 2-stage nuclear fusion rocket. The first stage would burn for about 2.05 years, accelerating the spacecraft to about 7.1% of light speed. Then it would be jettisoned. The second stage would burn for about 1.76 years more, bringing the final velocity to roughly 12% of light speed. At that speed, the journey to Barnard's star would take about 50 years. Add a few years for acceleration, and you're looking at around 54 years total. The people who launched it might still be alive when it arrived, though they would be old. The Daedalus design was enormous. The spacecraft would weigh about 54,000 tons at launch. Most of that would be fuel, 50,000 tons of deuterium and helium-3 to power the fusion reactors. The payload, the actual scientific instruments, would be only about 500 tons, less than 1% of the total mass. This illustrates the tyranny of the rocket equation perfectly. To carry 500 tons of instruments, you need 50,000 tons of fuel, a ratio of 100 to 1. And that's with nuclear fusion, one of the most efficient propulsion methods we can even imagine. Project Daedalus was never built. It was a design study, an exploration of what might be possible. But it was serious. The British Interplanetary Society spent years on it. They calculated trajectories, designed engines, figured out how to manufacture helium-3, which doesn't exist naturally on Earth in any significant quantity. You would have to mine it from the atmospheres of gas giant planets or from the surface of the moon. The conclusion was that Project Daedalus was theoretically possible. Nothing in the design violated known physics. But it would require an enormous commitment of resources and decades of technological development. We would need to master fusion propulsion. We would need infrastructure in the outer solar system to mine helium-3. We would need the ability to construct massive structures in space. None of this exists today, and we are not close to having it. In the 1980s and 1990s, there was Project Longshot. This was another design study for an interstellar probe. Longshot was designed to reach Alpha Centauri, the nearest star system, about 4.37 light-years away. It would use a fusion rocket burning deuterium and helium-3, similar in principle to Daedalus. But Longshot was smaller and slower. It would reach about 4.5% of light speed and make the journey in about 100 years. Again, the design was feasible in principle but far beyond our current capabilities. In the 21st century, there have been new proposals. Project Icarus, started in 2009, was a redesign of Project Daedalus using more modern technology and updated knowledge. The goal was the same: design an unmanned interstellar probe that could reach a nearby star within a century. Icarus incorporated improvements in materials, propulsion concepts, and scientific instruments that weren't available in the 1970s. The result was a similar design but more efficient. Still massive, still requiring fusion propulsion, still far beyond what we can actually build today. Then there's Breakthrough Starshot, which I mentioned earlier. This one is different from the others because it is actively being worked on right now, with real funding and real research teams. Breakthrough Starshot, announced in 2016, is funded by billionaire Yuri Milner and was supported by physicist Stephen Hawking before his death. The plan is to send thousands of tiny spacecraft, each weighing about a gram, to Alpha Centauri. These spacecraft would carry light sails a few meters across. A powerful ground-based laser array would shine on the sails, accelerating the spacecraft to about 20% of light speed in a matter of minutes. The journey to Alpha Centauri would take about 20 years. Add another 4 years for the data to crawl back at light speed, and you're looking at about 24 years from launch to receiving the first images. This is exciting because it is actually achievable using technology that's reasonably close to what we have now. The challenges are significant but not insurmountable. The lasers need to be powerful, but we are building increasingly powerful lasers for other purposes. The sails need to be lightweight and reflective, but we are developing advanced materials. The spacecraft need to be miniaturized, but we are getting better at building tiny electronics every year. The biggest challenge might be aiming. When you're accelerating a tiny spacecraft to 20% of light speed using a laser beam, you need to keep that beam focused on the sail throughout the entire acceleration period. The spacecraft is moving faster and faster, and the beam needs to track it precisely. Even a tiny error in aim would cause the spacecraft to veer off course, or the beam to miss the sail entirely. But these are engineering challenges, not fundamental physics problems. People are working on solutions. If Breakthrough Starshot succeeds, it would be humanity's first interstellar mission. A tiny probe weighing a single gram would cross 4.37 light-years in 20 years. It would send back pictures of the Alpha Centauri system, close-up images of any planets there, data about the system's composition and properties. And all of this would happen within the lifetime of the people who launched it. That is genuinely exciting. It's a real step toward interstellar exploration, even if it's a small one. But notice what Breakthrough Starshot cannot do. It cannot send humans. It cannot slow down at its destination. It cannot carry significant scientific instruments. It is a flyby mission, racing past at 20% of light speed, snapping pictures for a few minutes, then continuing into the darkness on the other side. It's better than nothing, but it is not the kind of exploration science fiction has trained us to expect. We are not sending astronauts to land on an exoplanet and study it up close. We are sending a camera the size of a microchip, flying past at 60 million miles per hour, hoping to catch a few good frames before it's gone forever. This is the reality of interstellar exploration with anything close to current technology. Small probes, fast flybys, no humans, no sample return, no long-term study. Just a quick glimpse as we race past at a fraction of light speed. And even this requires decades of development and billions of dollars in funding. Now let's think about the human element more deeply. Suppose we did build a generation ship. Suppose we solved every technical problem and dispatched a crew of 1,000 people to a star 10 light-years away. At 1% of light speed, the journey would take 1,000 years. That's about 30 generations. What would life actually be like aboard that ship? For the first generation, the volunteers, there would be excitement. They are pioneers. They are explorers. They are part of humanity's greatest adventure. They are leaving Earth behind to ensure humanity's future among the stars. There is purpose and meaning in that. But they know they will never see the destination. They will spend their entire lives aboard the ship, working to keep it running, raising children who will continue the mission they started but cannot finish. The second generation, born aboard the ship, never chose any of this. They were born into the mission. Earth is a story their parents tell them, a place they have never seen and never will. The ship is their entire world. By the third or fourth generation, Earth is ancient history. It is a mythical place, the cradle of humanity, but not home. Home is the ship. By the 10th generation, Earth might seem as distant and unreal as Atlantis does to us. A story, possibly true, possibly embellished over the centuries. By the 20th generation, the mission itself might have evolved. The descendants might no longer care about reaching the destination. They have built a culture aboard the ship. They have their own traditions, their own conflicts, their own concerns that have nothing to do with the abstract goal of arriving somewhere their distant ancestors planned long before any of them were born. The destination, when it finally arrives, might be a complete shock. The crew has been living in the controlled environment of the ship for 30 generations. Now they are being asked to step out onto an alien planet with strange gravity, unfamiliar atmosphere, unknown microorganisms, and unpredictable weather. They might not even want to leave the ship. They might choose to remain in orbit, sending down robotic probes to study the planet, but never actually setting foot on it. The ship has become their homeland. The planet, the supposed destination, is just another foreign place they would rather observe from a distance. This is one of the fascinating philosophical implications of interstellar travel. The mission you launch is not necessarily the mission that arrives. The people who depart are not the people who arrive. The goal you set may not be the goal that ultimately matters. Whatever culture launches the ship might be as different from the culture that arrives as ancient Sumerians are from modern New Yorkers. Sumerians sent texts that we can barely understand today, even though we share the same species and the same biology. Imagine trying to follow the instructions of people 30 generations dead, when the entire context of their civilization has dissolved. Now let's go back to the speed of light itself, because there's something deeper to say about it. The speed of light isn't just a property of light. It's a fundamental property of the universe, the maximum speed at which any information can propagate through space. It's the speed of causality itself. In special relativity, the speed of light is the conversion factor between space and time. It's what makes space-time a unified four-dimensional structure rather than separate three-dimensional space and one-dimensional time. The fact that the speed of light is finite and has the specific value it has is fundamental to how the universe works. If the speed of light were infinite, the universe would be entirely different. Cause and effect would be simultaneous across any distance. There would be no light travel time, no delay between events. The entire structure of physics would have to be rewritten. If the speed of light were slower, say 1,000 miles per second instead of 186,000, interstellar travel would be even more impossible. Light would take tens of thousands of years to cross a light year, if we still called it that. If the speed of light were faster, say 1,000,000 miles per second, the universe would be smaller in a sense. Light would cross distances more quickly. Time dilation effects would occur at higher speeds. But the fundamental barrier would still exist. You still couldn't exceed the speed of light, whatever it happened to be. The constant would just have a different number. The point is that we are stuck with the universe we have. The speed of light is what it is because of the fundamental constants of physics, the strength of electromagnetic forces, the permeability of free space, the permittivity of free space. These constants determine the speed of light. Change those constants, and you would change the universe in fundamental ways. You might not even have atoms or stars or planets. You might not have any structure at all. So we cannot wish for a faster speed of light. We have to operate within the constraints of the universe we inhabit. And in this universe, 1 light year is a vast distance that takes light 1 full year to cross. For anything moving slower than light, which is everything possessing mass, it takes longer. Much longer if you are using technology anywhere close to what we currently have. There is something philosophically profound about this. The universe has built-in limitations. There are places we can see but can never reach, even in principle. There are events occurring right now in distant galaxies that we will not see for millions or billions of years. By the time the light from those events reaches us, the events themselves are ancient history. The stars we see in the night sky, we are seeing them as they were years or centuries or millennia ago, not as they are now. Betelgeuse, the red supergiant in Orion, is about 550 light-years away. The light we see from Betelgeuse tonight left that star in the year 1474, around the time of the Renaissance. If Betelgeuse exploded as a supernova last week, we won't know about it for another 550 years. The information travels at the speed of light. And the speed of light is finite. This means the universe has a kind of cosmic horizon. Not just in space, but in time. There are events occurring beyond our cosmic horizon that we will never know about, because the light from them will never reach us. The universe is expanding, and the expansion is accelerating. Distant galaxies are moving away from us faster than the speed of light, because space itself is expanding between us and them. Light from those galaxies will never reach us. We can never know what happens there. We can never travel there. Those parts of the universe are fundamentally inaccessible to us, now and forever. This is the cosmic horizon, and it's shrinking. As the universe continues to expand and accelerate, more and more galaxies will cross beyond the horizon. Billions of years from now, observers in our galaxy will only be able to see our local group of galaxies. Everything else will have receded beyond the cosmic horizon. The universe will appear smaller, lonelier. Unless they have historical records from our era, future astronomers might not even know that there are billions of other galaxies out there. They will think the universe is just the local group, a few dozen galaxies in an otherwise empty void. This is humbling. We live in a special time, when the universe is still young enough and the expansion has not progressed so far that we can still see billions of galaxies. We can still study the cosmic microwave background, the afterglow of the Big Bang itself. We can still observe the large-scale structure of the universe. Future civilizations, if they exist at all, will not have that privilege. So in a sense, we should appreciate the view we have right now. We can see farther and know more about the universe than any future civilization will be able to. Even if we can never travel to those distant galaxies, we can at least observe them, study them, learn from them. That is something. Now, let's circle back to the question of why we even care about traveling 1 light year, or any interstellar distance at all. Why does it matter? What's the motivation for wanting to reach other stars? One reason is survival. Earth won't last forever. In about 1 billion years, the sun will have brightened enough that Earth's oceans will boil away. The planet will become uninhabitable for complex life. In about 5 billion years, the sun will swell into a red giant, possibly engulfing Earth entirely. Even if Earth survives that expansion, it will be a scorched, lifeless husk. If humanity wants to survive beyond those timescales, we will need to leave the solar system. We will need to find new homes around other stars. But 1 billion years is a long time. All of recorded human history is only about 5,000 years. 1 billion years is 200,000 times longer. There is no urgency. We have plenty of time to develop the technology we will need. Another reason is curiosity. We want to know what's out there. Are there planets like Earth around other stars? We already know there are planets. We have detected thousands of exoplanets using telescopes. But are any of them habitable? Do any of them harbor life? The only way to know for certain is to go there and look. Telescopes can tell us a great deal, but there are limits to what we can learn from light years away. We can analyze the spectra of an exoplanet's atmosphere and look for biosignatures, chemical indicators that life might be present. But we cannot be certain without visiting. There could be microbial life that doesn't produce detectable biosignatures. There could be complex life that we miss because we are searching for the wrong signs. The only way to be absolutely sure is to send a probe, or better yet, send humans. But, as we have established, sending anything to another star is incredibly difficult. So we are left with a frustrating situation. We know there are thousands of planets out there, some of them probably Earth-like, some of them possibly inhabited, but we cannot reach them. We can only look from a distance and wonder. It's like being a child standing outside a candy store, seeing all the sweets inside, but the door is locked and you don't have the key. The candy is right there, you can see it, but you cannot have it. That is humanity's relationship with the stars. We can see them. We can study them. But we cannot reach them, at least not with anything close to current technology. Maybe that will change. Maybe in a few centuries we will have fusion drives or antimatter engines, or something we have not yet conceived. Maybe we will send generation ships to nearby stars, slowly building a network of human colonies across the galaxy. Maybe we will discover new physics that allows faster-than-light travel, though that seems profoundly unlikely. Or maybe we will never leave the solar system. Maybe the distances are just too great, and the resources required are simply too vast. Maybe we will build a thriving civilization within the solar system, billions of people living in space habitats and on terraformed moons, but never venturing to the stars. Both futures are possible. We don't know which one we will get. What we do know is that right now, today, traveling 1 light year is effectively impossible. It would take over 1,000 years with our fastest spacecraft. It would take decades or centuries with optimistic future technology. It would require energy levels and engineering capabilities far beyond what we currently possess. 1 light year is a tiny distance on cosmic scales. It is less than the distance to the nearest star. But it is vast by human standards. It is a distance that might as well be infinite, given our current limitations. And that is the reality we have to accept. We live in a universe where distances are immense and speeds are limited. We are slow creatures on a small planet, looking out at a cosmos we can observe but not physically traverse. It is humbling, it is frustrating, but it is also beautiful in its own way. The universe is vast and mysterious. There are wonders beyond counting, scattered across billions of light years. We will never see most of them in person. But we can imagine them. We can study them from a distance. We can dream about them. And maybe that is enough. Maybe the journey isn't about physically reaching the stars. Maybe it's about reaching for understanding, pushing the boundaries of knowledge as far as we can, learning everything we can about this incredible universe we find ourselves inside. Because even though we cannot travel 1 light year in a human lifetime, we have already explored the universe in ways that genuinely matter. We have mapped galaxies billions of light years away. We have detected gravitational waves from black holes colliding in the distant past. We have observed the cosmic microwave background, light from when the universe was only 380,000 years old. We have discovered thousands of exoplanets and learned that planets are common throughout the galaxy. We have developed a mathematical description of the universe spanning from its first moments to its ultimate fate. We have done all of this without leaving Earth, or at most, without going farther than the moon. Our bodies might be confined to this small corner of space, but our minds, our understanding, our knowledge, they have traveled farther than any spacecraft ever could. And in the end, that might be the most important journey of all. Let me give you some more ways to grasp just how impossibly distant 1 light-year really is. We have talked about time, about how long it takes to travel that distance. But let's talk about it in terms of scale, in ways that might make it more concrete in your gut. If you could drive a car at highway speed, 60 miles per hour, continuously without stopping, how long would it take to drive 1 light-year? 1 light-year is 5.878 trillion miles. Divide that by 60 miles per hour. That gives you about 97.97 billion hours. Convert to years. That's about 11.18 million years, over 11 million years of continuous driving. Modern humans have only existed for about 300,000 years. You would need to have started driving before modern humans even evolved. You would need to have been driving when our ancestors were still Homo erectus, a different species entirely, when there were no cars, no roads, no wheels, no civilization of any kind, when humans were just beginning to use stone tools and control fire. And you would still be driving today, and you would still have millions of years left to go. That's 1 light-year at 60 miles per hour. What if you could walk? The average walking pace is about 3 miles per hour. At that rate, walking 1 light-year would take about 222.36 million years. That's longer than the time since the dinosaurs went extinct. The asteroid that killed the dinosaurs struck Earth about 66 million years ago. You would need to walk more than 3 times longer than that. You would need to have started walking before there were any primates, before there were any mammals larger than a shrew, when dinosaurs still ruled the Earth, and you would still be walking today. And you would still have over 150 million years left to go. What if you could run? A marathon runner sustains about 6 miles per hour for over 26 miles. That is faster than walking, but slower than driving. At 6 miles per hour, running 1 light-year would take about 111.18 million years, still longer than the age of the dinosaurs. What if you took the fastest commercial airliner? A Boeing 747 cruises at about 570 miles per hour. At that speed, flying 1 light-year would take about 1.176 million years. We are back to timescales longer than modern humans have existed. Every form of transportation we have, from walking to the fastest jets, is pathetically slow compared to the distances between stars. Even our fastest spacecraft, the Parker Solar Probe at 430,000 miles per hour, would take 560 years. Let's think about this another way. Light can circle Earth's equator about 7.5 times in 1 second. In that same second, how far does our fastest spacecraft travel? The Parker Solar Probe travels about 119 miles in 1 second. Light travels about 186,000 miles in that same second. Light is about 560 times faster than our fastest spacecraft. That is the gap we are trying to bridge. We are not even close. We are not within an order of magnitude. We are not within 2 orders of magnitude. We are off by more than a factor of 1,000. Here's another comparison. The distance from Earth to the Moon is about 238,900 miles. Light takes about 1.3 seconds to travel from Earth to the Moon. Radio signals traveling at light speed take about 1.3 seconds to reach the Moon. That is why there is a noticeable delay in conversations between astronauts on the Moon and mission control on Earth. The Parker Solar Probe would take about 33 minutes to travel from Earth to the Moon. Now compare that to 1 light-year. 1 light-year is about 24.665 trillion times the distance from Earth to the Moon. That is a number so large it is hard even to comprehend. If you could line up 24.665 trillion Moon-Earth distances end to end, you would have 1 light-year. Here's another way to think about it. The distance from Earth to the Sun is about 93 million miles. We call this distance 1 astronomical unit, or 1 astronomical unit. Light takes about 8 minutes and 20 seconds to travel 1 astronomical unit. If the sun suddenly disappeared, we would not know about it for 8 minutes and 20 seconds, because the information would travel at the speed of light. The Parker Solar Probe would take about 9 days to travel 1 astronomical unit at its maximum speed. 1 light year is about 63,241 astronomical units. 63,241 times the distance from Earth to the Sun. If you made a scale model where Earth and the Sun were 1 inch apart, how far away would you have to place an object to represent 1 light year? 63,241 inches. That's about 5,270 feet, about 1 mile. So on a scale where Earth and the Sun are 1 inch apart, 1 light year is about a mile away. And the nearest star, Proxima Centauri, is 4.24 miles away on that same scale. The center of the Milky Way is about 26,000 miles away. The Andromeda Galaxy is 2.5 million miles away. These scales are hard to wrap your mind around. No matter how you slice it, 1 light year is vast. It is a distance that dwarfs anything we experience in everyday life. It is a distance that dwarfs the entire solar system. Neptune, the outermost planet, orbits at about 30 AU from the Sun. 1 light year is 108 times the distance from the Sun to Neptune. If Neptune's orbit were 1 inch in diameter, 1 light year would be 175 feet away. That's the height of a 15-story building. Now let's think about what it would actually be like if we could travel 1 light year. Suppose you boarded a spacecraft capable of traveling at 50% of light speed. You would reach your destination in 2 years of ship time, though more time would pass on Earth due to time dilation. What would you see along the way? As you accelerated, the stars behind you would shift in color. Light from stars behind you would be red-shifted as you moved away from them. Light from stars ahead of you would be blue-shifted as you moved toward them. This is the relativistic Doppler effect. As you approached 50% light speed, the shifts would become dramatic. Stars ahead would appear bluer and brighter. Stars behind would appear redder and dimmer. The distribution of stars in the sky would appear to change. More stars would seem to concentrate ahead of you, fewer behind. This is called relativistic beaming, sometimes nicknamed the headlight effect. The faster you go, the more pronounced it becomes. At 90% of light speed, almost all the starlight would appear to be coming from a small cone ahead of you. The stars behind and to the sides would appear to dim almost to invisibility. The sky would compress into a glowing tunnel. As you traveled, nearby stars would show parallax. Their positions relative to distant background stars would shift as you passed them. At 50% light speed, covering half a light year in 1 year, nearby stars would noticeably change position. Stars that had been ahead of you would slide past to the side and then behind. Stars that had been to the side would shift to behind you. New stars would appear ahead. You would see the constellations change. Familiar patterns would distort and eventually become unrecognizable. The Big Dipper, Orion, Cassiopeia, all the constellations you had known would shift and morph. New patterns would emerge. And when you arrived, 1 light year away from where you started, the night sky would be completely different. Earth's sun would be just another star among thousands. Not particularly bright, not especially remarkable, just one more point of light in the darkness. If you had a powerful enough telescope, you could look back and see the solar system. You could see the planets, tiny dots of reflected light orbiting a yellow star. You could see Earth, a pale blue dot like the famous Voyager photograph, but from a different angle. You might feel the isolation. You would be farther from home than any human has ever been. Farther than the moon, farther than Mars, farther than any planet. You would be in interstellar space, in the vast darkness between stars. The nearest star to you might be several light years away. You would be utterly alone, surrounded by emptiness, with no hope of rescue if anything went wrong. This is the reality of interstellar travel. Even if we could travel at high fractions of light speed, even if the journey only took a few years, it would be a profound psychological challenge. The isolation would be absolute. The distance would be incomprehensible. The risk would be enormous. And yet some people would probably volunteer for it. Throughout history, Humans have always been explorers. We have crossed oceans in wooden boats, not knowing what lay on the other side. We have climbed mountains because they were there. We have explored caves, deserts, polar ice caps, the deepest parts of the ocean. We have sent astronauts to the moon, knowing the risks. When given the chance, some humans always choose to explore, to push boundaries, to see what lies over the next horizon. If we ever develop the technology to travel to other stars, there will be volunteers. People willing to leave everything behind, knowing they might never return, for the chance to see something no human has ever seen, to set foot on a planet orbiting another star, to be the first. That drive, that curiosity, that willingness to risk everything for discovery, that is one of humanity's defining traits. It has carried us from small tribes in Africa to a global civilization. It has carried us to the moon and sent our robots to every planet in the solar system. Maybe someday it will carry us to the stars. But that day is not today. Today, 1 light-year remains an impossible distance. Now let's talk about what we have actually accomplished despite these limitations. In the last few decades, we have discovered thousands of exoplanets, planets orbiting stars other than the Sun. Before 1992, we did not know of a single planet outside our solar system. We suspected they existed, but we had no proof. Then, in 1992, astronomers discovered the first confirmed exoplanets orbiting a pulsar. In 1995, they discovered the first planet orbiting a Sun-like star, 51 Pegasi b. Since then, we have found thousands more. As of the most recent counts, we know of over 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. We have found planets of every type imaginable: hot Jupiters, giant planets orbiting close to their stars, heated to thousands of degrees, ice giants like Neptune, but circling other stars, rocky planets like Earth, some of them in their stars, habitable zones, where liquid water could potentially exist, super-Earths, rocky planets larger than Earth but smaller than Neptune, mini-Neptunes, planets between Earth and Neptune in size. We have found planets orbiting binary star systems, something that was once thought to be impossible. We have found planets orbiting the remnants of dead stars. We have found planets orbiting their stars backwards, in retrograde orbits. We have found planets that are pitch black, absorbing nearly all the light that strikes them. We have found planets that might rain glass sideways due to their extreme winds. We have found planets that might host oceans of liquid lava. We have even found a few planets that might be genuinely Earth-like, rocky planets about Earth's size, orbiting in the habitable zones of Sun-like stars, where temperatures might allow liquid water on the surface. Planets like Proxima Centauri b, orbiting the nearest star to our Sun. Planets in the TRAPPIST-1 system, where 7 Earth-sized worlds orbit a small red dwarf star, 3 of them in the habitable zone. Planets around Kepler 442, KEPLER 452, and dozens of other stars. We don't know if any of these planets actually harbor life. We cannot see them clearly enough to know. They are too far away. They are too small and dim compared to their stars. But we are working on it. The James Webb Space Telescope, launched in 2021, is analyzing the atmospheres of exoplanets. By studying how starlight filters through a planet's atmosphere during a transit, when the planet passes in front of its star, we can determine what gases are present: oxygen, methane, water vapor, carbon dioxide. All of these leave distinct signatures in the spectrum. If we find oxygen and methane together in an exoplanet atmosphere, that might indicate life. On Earth, oxygen and methane don't naturally coexist. Oxygen reacts with methane and destroys it. The only reason we have both in Earth's atmosphere is that living organisms constantly produce both. Plants produce oxygen. Bacteria, cows, and other organisms produce methane. Without life continuously replenishing both gases, they would react and disappear. So if we find a planet with both oxygen and methane in its atmosphere, that's a strong hint that something is producing those gases. That something might be life. We have not found such a planet yet, but we are looking. And the fact that we are looking that we are analyzing the atmospheres of planets orbiting stars dozens or hundreds of light years away is genuinely remarkable. We cannot go there. We cannot send a probe. We cannot travel 1 light year, let alone dozens or hundreds. But we can study those planets from here. We can learn about them. We can search for signs of life. And if we find it, if we discover life on another world, it will be one of the most profound discoveries in human history. Even if we can never go there, even if we can never meet whatever forms of life might exist, just knowing that life exists elsewhere would change everything. It would tell us that we are not alone. It would tell us that life is not a cosmic fluke, a one-time accident that happened only on Earth. It would tell us that the universe is teeming with life, that wherever conditions are right, life finds a way. And maybe someday, we will find intelligent life. Maybe we will detect radio signals from a distant civilization. Maybe we will see the signatures of technology, heat signatures from megastructures, or unusual spectral lines from industrial pollution. Maybe we will find evidence that we are not the only species that has built a civilization, that has looked up at the stars and wondered. And if we do, what then? We still cannot travel to them. If they are 100 light years away, any message we send will take 100 years to reach them. Their reply will take another 100 years to come back. A single exchange of messages would take 200 years. Everyone involved in sending the first message would be dead before the reply arrived. But maybe that's all right. Maybe just knowing they are there is enough. Maybe the conversation itself, spanning centuries, is valuable, even if no individual experiences both sides of it. Humanity could have a dialogue with another civilization, exchanging ideas and information over thousands of years. Our great-great-great-grandchildren would receive the messages we sent. Their great-great-great-grandchildren would receive our replies. It would be a conversation unlike any other in human history. Slow, patient, spanning generations, but real. This is the kind of future we might actually have. Not Star Trek, with ships zipping between stars in days or weeks. Not Star Wars, with hyperspace jumps across the galaxy. But a future where we are connected by light, by radio waves, by information traveling at the speed of light between stars. Where we explore the universe not with our bodies but with our telescopes and our minds. Where we search for life, for intelligence, for understanding across vast distances we can never physically cross. It is not as exciting as science fiction, but it is real. And there is a beauty in that. A beauty in accepting the limitations of the universe and finding ways to work within them. A beauty in recognizing that we don't need to travel to the stars to explore them. We just need to look, to listen, to learn. So when someone asks how long it would take to travel 1 light year, the answer is both simple and complex. With our current technology, over 1,000 years. With near-future technology, perhaps decades to centuries. With far-future technology that may never exist, perhaps years. But the deeper answer is that maybe we don't need to travel 1 light year. Maybe we can accomplish everything that matters without leaving home. We can study the universe from here. We can search for life from here. We can expand our knowledge and understanding from here. We can build a civilization in our solar system. From here, we can ensure humanity's survival by spreading to multiple worlds within our own solar system. We can create art, science, culture, meaning, purpose, all from here. And maybe that's enough. Maybe the stars don't need to be destinations. Maybe they can simply be inspirations. Points of light in the sky that remind us how vast the universe is, how small we are, how much there is to learn and discover. 1 light year is an impossible distance, but it is also just a measure, a unit we invented to describe the space between stars. The distance itself hasn't changed. The stars have always been this far away. What has changed is our understanding. We have learned how far they are. We have measured the distance. We have done the math and realized just how long it would take to get there. And in doing so, we have learned something about ourselves. We have learned that we are bound to this corner of space, at least for now. We have learned that the universe is bigger than our ambitions. We have learned humility. But we have also learned something else. We have learned that even with these limitations, we can still accomplish remarkable things. We can still explore, we can still discover, we can still push the boundaries of knowledge. Just because we cannot physically travel 1 light year doesn't mean we cannot reach across 1 light year. Our telescopes can see across light years, our radio dishes can listen across light years. Our minds can comprehend concepts that span light years. We have already crossed that distance in every way that matters, except physically. And maybe, in the end, that's the real achievement, not building faster ships, not finding loopholes in physics, but expanding our understanding to encompass distances we can never personally traverse. That is the human story. We are creatures who evolved on one small planet, adapted to think about distances measured in miles and times measured in days. But we have taught ourselves to think about light years and millions of years. We have stretched our minds to encompass the cosmic scale. We have made the infinite comprehensible, and that is worth celebrating. So yes, it would take over 1,000 years to travel 1 light year with current technology. Yes, the stars are unreachable with anything we can build today. Yes, the universe is vast, and we are small and slow. But we are also curious and intelligent and persistent. We are also dreamers and explorers and learners. We are also the species that looked up at the night sky and asked, how far away are those stars? And then figured it out. We measured distances so vast they boggle the mind. We calculated travel times that span millions of years. We designed spacecraft that exist only on paper but could theoretically cross interstellar space. We searched for planets around other stars and found thousands. We are searching for life in the universe, and maybe one day we will find it. We have done all of this from one small planet, using nothing but our minds and the tools we have built. And that is incredible. That is worth more than any physical journey could ever be. Because the journey isn't about traveling 1 light year. The journey is about understanding what 1 light year means. The journey is about grasping the scale of the universe. The journey is about looking up at the night sky with both knowledge and wonder. The journey is about being here, now, in this moment, on this planet, looking out at the cosmos and comprehending our place in it. And that journey, that intellectual and spiritual journey, is one we can all take right here, right now, without traveling a single mile. That is the real answer to how long it takes to travel 1 light year. In body, thousands of years. In mind, an instant.